morning. I'm Carrie Moss Stearns. Welcome to this news briefing from the 251st National Meeting and Exposition of the American Chemical Society in San Diego. We are joined today by Dr. Albert F. Yee, Mary Nora Dickson, and Elena Liang from the University of California, Irvine. They will be talking to us about how cicadas and dragonflies might someday save your sight. Dr. Yee?
Well, we were doing some research on nano-patterned surfaces for corneal applications when we came across some very interesting literature on how the wings of cicada could kill bacteria. And I'm going to hand this over to my students, Mary and Elena, to talk about their experience in using these insect wings to inspire their work.
Great, thank you, Dr. Yee. So the goal of our work was to be able to make polymer surfaces antibacterial without introducing any type of chemical modification. And so Professor Yee and the other researchers in the group found this work where the cicada's wings and dragonfly wings actually have teeny tiny spikes on the top. These nanospikes are a lot smaller than bacteria, and it was found that when bacteria land on the surface of the wing, they actually conform themselves to the tips of these pillars. And in doing so, they change the shape of their cell wall, and they eventually contort themselves into such an unfavorable position that they rupture. So this group in Australia made this discovery. And when our group saw it, Professor Yee thought, hey, we could do that. He had been working on a technique called Nano imprint lithography in the early 2000s, and this technique was developed primarily for the semiconductor industry. And so using this technique, you can create tiny surface texture or surface roughness with a very precise geometry, and you can create it over a very large area. And so the way it works is you can purchase a commercial mold, let's say a mold that has small holes in it, an array of holes, and you press it under heat and pressure into a polymer film. And in doing so, when you release it, you're left with a polymer film that has spikes everywhere, all over the surface. And so this technique was both industrially scalable, commercially available, and it was ready to go. And so using this, we're able to make ordinary FDA-approved polymer surfaces have the same type of nanospikes that are on the cicada's wing. And we found that ordinary PMMA, which is also known as plexiglass, could kill E. coli bacteria without any special chemical modifications. So the main advantage of that is that it may help reduce the risk for resistance, antibiotic resistance, and it could help protect patients from having to take antibiotic drops.
Right, and then the great thing about this technology is that we can also apply it to how the mammalian cells would behave on the surface, since we are looking to medical device applications. And so we found so far that similar nanostructures, while they kill the bacteria, the cells are actually still alive, but they are forced to move to a different area where they could try to find a place where they can adhere better. And so we can use these physical surface nano modifications to control where the cells could be adhering onto the surface of our implants. And we're working towards creating an artificial cornea implant where we apply the same methodology, where we have cells that would adhere to part of the implant to improve the integration in the patient's eye, while preventing cells from sticking in a certain area so that the patient can still see through the device.
Do we have any questions? When you get the microphone, please state your name and affiliation.
Sam Tracy, Chemistry World. How robust are these surfaces? Do they last longer or less long than, say, an antibacterial film?
Well, do you want to take?
Go ahead.
We haven't done a durability study yet, per se. So far, our studies have just been for 24 hours under liquid media. However, one problem with a chemical antibiotic is that the concentration will slowly decrease over time, and it can also vary over space. So the farther you move away from the surface, the lower the antibiotic concentration. So in theory, these surfaces should be very long-lasting because there's no chemical that can run out over time.
But we are looking into long-term studies. So for the mammalian cell work, we did let them adhere for about 72 hours, and then we did see under SEM that the structures are still intact.
And from the semiconductor work, do they last a long time, or do they erode down with wear?
I'm sorry, I didn't get that.
So these spikes, are they fragile? That would be the concern, that they would wear down with time, but perhaps in the semiconductor industry they find that they're actually very robust and potentially are a much better solution than the film.
Well, okay, the structures we made for semiconductors have somewhat different surface features. For these antibacterial or cell control surfaces, the nanopillars need to have a very spiky shape in order to penetrate with the bacteria. And the fabrication technique is somewhat different. But in semiconductors, you don't need these very spiky structures, except perhaps in solar cells. And so those surfaces are much less susceptible to mechanical damage. And on top of that, most of these are usually protected, because in present-day semiconductor devices, you very rarely have single level. They have multiple levels. So these structures are not susceptible to damage.
So it's Kath O'Driscoll from Chemistry and Industry magazine. The press release also talks about the fact that you've looked at both cicada and you've looked at dragonfly wings as well. Can you explain a little bit about the difference? Do you need to use pillars of both types, the dragonfly and the cicada, in order to be broad spectrum, have a broad spectrum antibacterial effect?
No, we don't believe so, but I'll ask Mary to answer this.
Certainly. So the dragonfly pillars are actually a little bit taller and a little bit skinnier, so it seems like they're sharper. So the original paper that discovered the effectiveness of the dragonfly wings was actually a follow-up to the cicada wing, and it seemed like it could do everything the cicada wing can do, but better. And so our recent work in the lab has just focused on making just the sharper and taller pillars.
Okay. And I'm just interested, I actually have artificial lenses myself, which was a fantastic, but there was a very tedious procedure of antibiotics for about 2 weeks.
Right.
So, but the only thing that sort of interests me is about your research is it implies that these bacteria kind of get impaled on the spikes. Do they get washed away in some way, or do they degrade over time? What happens to them? It's kind of just an interesting idea that, bacteria land on them. I mean, what happens once they rupture? Do you get a constant buildup of bacteria?
Right. So at least for the artificial cornea, because you're constantly blinking, so we believe that with just blinking, the bacteria or the cells that would not adhere very well will just come off and wash away with your tears. We're actually also looking into other ways to prevent the buildup, but the idea is with our nanostructures, potentially we would decrease the amount of cells that would adhere in the first place, or that could adhere on these structures, and so we're aiming that if we just prevent the initial adhesion, then we could potentially prevent the biofilm buildup.
And also just about
Right, so perhaps one thing that needs to be emphasized is that the surfaces are not just bactericidal, they also actually prevent bacteria from adhering in the first place. So when you compare the flat surface against these nanostructured surfaces, you see very, very, very few bacteria or cells. And then the bacteria that are there are dead, mostly. And we think that when you're blinking, you are actually washing away, because when you're blinking, there's actually a tear film that moves very rapidly over the corneal surface. And the shear rate that's involved is exceedingly high, and so we think that it would blink away, literally, the debris that might accumulate on the surface.
When do you expect to go to preclinical tests with these lenses?
Right. We are currently conducting an implantation study using lens shapes that do not yet have the nanopillars, just to see what is the geometry that's the most suitable for implantation, so that it will involve the least amount of cutting and suturing. While this is going on, we're also studying how to make the nanostructures on a curved surface. And for this, I'm going to ask Elena to explain that.
On the curved surface?
Yeah.
Yes. So there's another imprinting process where we have our polymer, we actually put the polymer structures directly on top of the curved surface. It's very similar to nano imprinting. It's just that we start off with the structures on the curved surface.
Mary, you want to amend?
Sure. Well, so as you can imagine, the molds that we're buying are flat. They're planar. And so we have these planar molds, and then right now we have flat polymer films, and we can simply just do the imprinting to transfer the structures. But when we want to use a curved device, we actually have to use a flexible mold that has the holes in it. And so we put a polymer solution into the holes, and then we can bend this flexible mold over the top of the curved surface of the lens. And so that's how we're able to transfer structures onto a curved surface. And I think that's the first time that's been done. So we're pretty excited about that.
And we have an online question.
This question is from Ko Kowalski for Science News for Students. And she has a question about other biomedical uses for these nanospikes. And she says, could you briefly explain how you get the cells you want to adhere to stick in the right place, and what do those cells do?
So it wouldn't be nanospikes that we would use another type of pattern. So there's been literature that's shown that line structures or grooves would improve cell adhesion or allow the cells to migrate and elongate on these structures. And so these would be the type of structures we would try to include with the integration of improving the cell adhesion onto the surfaces. In terms of other medical implants, that's the greatest thing about our technology. It's not just limited to the artificial cornea. We can see, because there's many other implants that will actually need control of cell adhesion. So we can imagine stents where you have to deal with the endothelial cells, the platelets. And it could also be applied for orthopedic applications as well.
This is Xifeng Liu from Department of Orthopedics, Mayo Clinic, Minnesota. I'm just wondering whether this kind of surface is bacteria specific to some specific bacteria, or it can inhibit all kind of bacteria. How many bacteria have you evaluated?
Yeah, that's a very good question. So the original study on dragonfly wings did look at several different types of bacteria, including gram-negative and gram-positive bacteria, and even spores, which have a very thick cell wall. Additionally, there was another study done with the dragonfly wings where they actually showed they could kill yeast cells as well. So we believe this actually could be a pretty broad method that could kill many different types of pathogens.
Sam Tracy, Chemistry World again. Treating the surfaces in this way, does it affect, is it visible that this affects, and do these optical properties, would they matter in a corneal implant?
So we actually stick with this nano-size range because we want to make sure that these structures are within the visible wavelength of light. And so our structures are in the sub-100 nanometer range. And so we have data where we show the transmittance of our structures compared to just flat PMMA, and we found that it's about the same.
Thank you. The archived version of this session will soon be posted at bit.ly/ACS Live San Diego. Please join us for our next press conference today at 10 a.m. on a new material to help fix damaged spines. Thank you.